What's up guys, my name is Rustagi and today I'm going to be teaching all of you guys Unit 9 of AB Calculus BC. So now before I begin, please go to the description right now and get my free AB Calculus AB and BC books, and those books have everything you need to know to get a 5 in your class. So now let's begin with Unit 9 of AB Calculus BC. So our first topic is defining and differentiating parametric equations. So a parametric equation involves continuous functions f and g, in which x equals to f of t while y equals to g of t, and then all xy coordinates can be represented as f of t, comma, g of t. And then differentiating this is a little more complicated, because if we want to find dy over dx, now this is equivalent to dy over dt divided by dx over dt, and the reason is that both y and x are functions of time. Now, what if we want to find the second derivative of a parametric equation? Well, we can do something similar. Now, to find the second derivative of a parametric equation, just memorize this formula. The second derivative can be represented as, in the numerator, you differentiate dy over dx, the expression you get with respect to time, and then you divide that by dx over dt. So to find the second derivative, you must first find dy over dx, which is the first derivative. Now, how do we find the arc length of curves given by parametric equations? Well, the arc length for non-parametric equations was basically the square root of 1 plus dy over dx squared from a to b. Now it's a little different. For parametric equations, the formula is from a to b, right? The integral bounds, and then the square root of that inside, dx over dt squared plus dy over dt squared. So you basically integrate that. Now, the derivative of vector-valued functions. Now, vector-valued functions will also be in the form of f of t, comma, g of t, where basically x and y are both functions of time. Now the derivative of the vector function can be found by simply differentiating f of t and g of t separately, and we get f prime of t, comma, g prime of t. However, if we want to find dy over dx, then we must do dy over dt divided by dx over dt, because again, both y and x are functions of time. Now, integrating vector value functions is relatively simple. You separately integrate x equals to f of t and y equals to g of t. Now, it's very important to be able to solve motion problems using parametric and vector value functions. This is very popular on the free response section. Well, if position is x of t, comma, y of t, then that means velocity is x prime of t, comma, y prime of t, because velocity is the derivative of position. So acceleration is the derivative of velocity, so it's x double prime of t, comma, y double prime of t. And then you will also be asked to determine the speed of a vector valued function, or even a parametric function. Now, the speed is basically the absolute value of velocity, and it's represented as the square root of x prime of t squared plus y prime squared. So basically you find, you differentiate your x and you differentiate your y separately with respect to time. After you differentiate both functions, you square them and then you square root that. Now the total distance traveled from time a to b can be found by integrating the speed, the expression for speed that I just showed you, with respect to time. Now, before I jump into some polar form, let's discuss how to convert a polar form, right, coordinate to rectangular form. Well, doing that is relatively simple. If we're given r, comma, theta, then that means x equals to r cosine theta and y equals to r sine of theta. So in rectangular form, it's simply r cosine theta, comma, r sine theta. Now let's do this in the reverse direction. If we're given a rectangular coordinate such as 3, 4, and we want to convert this to polar form, then first, we know that r equals to the square root of x squared plus y squared, since that's the distance from the origin. So we first find that. And then theta is the arctan of y over x. So in this situation, we can find that the radius, the r is 5, and then arctan of 4 over 3 is simply 0.93 radians. So in polar form, this can be written as 5, 0.93. Now I'm going to show you how to graph a polar function, since that's important. This is a review. So basically, you're going to graph out the simple angles of theta, such as 0, pi over 6, which is 30, pi over 3, which is 60, pi over 2, which is 90, pi, which is 180 degrees. Those are really simple angles to work with. So you find the points for that, and you graph it out. So closely look at this animation of me graphing out 3 minus 3 sine theta. Now, let's differentiate polar form. So a polar rate function is given as r equals to f of theta. So the derivative of a polar function is f prime of theta times sine of theta plus f of theta times cosine theta divided by f prime of theta times cosine theta minus f of theta times sine of theta. So please memorize this, and if you want to see how this is derived, check it out in my book. I have derived it there for you. Now, area bounded by a polar curve is a super popular topic. Now, sometimes you will be given a polar curve, right? And then you're going to be asked to find the area of that polar curve from the angles A and B, those radial lines, alpha to beta. Now, to do that, you simply use the formula 1/2 times the integral from alpha to beta of r squared, which is the polar function squared, with respect to theta. And you can simply integrate this, and usually it's done using a calculator. And this is very popular on both multiple choice sections and free response sections. And then integrating polar curves like limicons and roses. It works differently. You can't just blindly use this formula. It's different for some situations. And if you want to look at the differences, you need to check out my book. I have done it for the different types of polar curves. Now, this is an example of a polar curve, right? And what I've graphed out is the area between when theta equals to 0 and theta equals to pi over 6. And I'm showing you this so you can visualize how the area looks. Now, finding the area of the region bounded by two polar curves. Now, this is very important. Now you'll be working with two polar curves. And then, if you want to find the area that is contained in one polar curve but outside another one, then this is represented using the formula 1/2 times the integral from alpha to beta of one of the functions squared minus the other function squared with respect to theta. Now, to find the overlapping area between two polar curves, you should label the intersection points, and then you can connect the intersection points and then find the area of one side and then the other and the area of the other separately, and then you can add both areas to each other. Now, finding the area contained in one polar curve but outside another versus the overlapping area, they're both different things, and the method to find both areas is a little different. Now, let's look at a free response question from the 2004 AP Calculus BC exam. Now, please pause the video and closely read the problem before you continue. Well, by now I hope that you actually pause the video and try the problem. So let's look at the solution. For part A, we want to find the speed of the particle. So the speed of the particle is simply the square root of dx over dt squared plus dy over dt squared. So since this is a calculator-based free response question, we can easily find x prime of 0 plus y and y prime of 0. So we simply use a calculator to find that dx over dt at 0 is 3, and then dy over dt at 0 is 7. And then we can plug that in to get the square root of 3 squared plus 7 squared, which is the square root of 58. Now, to find the acceleration, which is also something we're asked in part A, we simply find the second derivative of x and y separately and plug in 0. And we can do that for this problem to simply get 0, negative 3. Now in part B, we want to find the equation of the line tangent to the path of the particle. So that means we first want to find dy over dx, which is the slope. And since this is a parametric equation, we know that dy over dx equals to dy over dt divided by dx over dt. And that means we want to find y prime of 0 divided by x prime of 0. So we simply plug in 0 into our expressions for dy over dt and dx over dt to get that dy over dx equals to 7 over 3. So that's the slope. So that means our equation for the tangent line can be represented as y equals to 7 over 3x plus b. And now let's find b, which is the y-intercept. Since we know that the particle is at the point 4, 1, we plug that point in. So x equals to 4 and y equals to 1. And we can solve that to find that b equals to minus 25 over 3. So we plug that into our equation to find that our final equation is y equals to 7 over 3x minus 25 over 3. Now in part C, we want to find the total distance that this particle travels from time t equals to 0 to time t equals to 3. So we simply use our formula. So we integrate the speed. So we integrate dx over dt squared plus dy over dt squared, all of that square rooted. So we plug in our expression for dx over dt and we plug in our expression for dy over dt, and we simply use our calculator. We put this all into our calculator and we can find that the distance is 45.226. Now in part D, we want to find the x-coordinate of the position of the particle at time t equals to 3. Well, we know that at time t equals to 0, the particle's x position is 4. Now we simply integrate dx over dt, which is the rate of change of the x position, right? And we integrate that from 0 to 3 to find how much the position has changed from time t equals to 0 to time t equals to 3. And then we add that to x of 0, which is the position at 0. So we can integrate the square root of t to the power 4 plus 9 from 0 to 3 using a calculator, and we can add both of these up to find that the position at time t equals to 3 is 17.93. Now, this is a very important question from an actual AP Calculus BC exam, and please pause the video and try it. Now, by now, I hope you actually paused the video, so now let's go over the solution immediately. So basically, we're given two polar curves, r equals to the square root of 2 and r equals to 2 cosine theta. And then we want to set up an expression, right, involving one or more integrals with respect to the polar angle theta that represents the area. Well, I already told you about how there's two different types of areas we can find. The area outside another polar curve but contained inside one, and the other is the overlapping area between two polar curves. Now, this problem, we want to find part of the overlapping area between the two curves. So in such problems, we first label the intersection point. So the intersection point is at 1, 1, so we label that. And then we connect that to the origin. Often in polar problems, connecting a point to the origin is extremely useful. So now we connect the point from 1, 1 to 0, 0. And now the green area that I just highlighted, that represents the area that is contained in the curve r equals to 2 cosine theta, from theta equals to pi over 4 to theta equals to pi. And then the red area represents the area of the curve r equals to square root of 2 from 0 to pi over 4. So since now I know the polar equations that need to be integrated and I know the integration bounds, I can represent the area for each separately using the formula that the area of a polar curve is 1/2 times the integral of r squared with respect to theta. So now I use that for both sections, and then I can sum both expressions up to write out this as the final expression, and I don't need to evaluate it. Now, thank you so much for watching this video, and please don't forget to like, share, and subscribe, since that's going to tell me that you guys are truly enjoying and learning from the books and the videos that I've been making for you guys. And don't forget to join the Discord server to meet other hardworking students that are preparing for various competitions and exams, such as the AP exams. And also, don't forget to follow the Instagram, if you have Instagram, to view educational reels and cool animations. And again, thank you so much for watching this video, and I really hope to see you soon back again on this channel.